Higher order derivatives. So because our derivative of a function is also a function, so here we say our y is equal to a function of x, here our derivative of y is also equal to a function of x. We can differentiate this function again, and we may be able to do this several times. So the first time we do this, differentiating our f of x, and we may put f dash x dy on dx, or we may put our y dash here. That's our first derivative. Our second derivative, it's a little bit harder to see here, gives us f dash dash x here, d squared y on dx squared, or we can say y dash dash. Here then we have 3 dashes x is our third derivative, and so on. 1, 2, 3. So we use a dash after our f or our y to denote the first derivative, 2 dashes for the second, and so on. Looking at our example here, we want to find the first 4 derivatives of the following equation. So here we can say our dy on dx here. 4 times 2 is 8, x3 minus 9x squared plus 6x minus 1. Then our next derivative here, we're going to end up with 24x squared minus 18x plus 6. And we're just following the same process again and again. Here, so we end up with 48x minus 18, and our fourth derivative we'll end up with just 48 here. So we have another example here, and again we're taking the first 4 derivatives. So here we're going to use different notation here, so we end up with 7x to the power of 6 minus 8x to the power of 3 plus 6x minus 2. Our second derivative, 42x to the power of 5 minus 24x squared plus 6. Our third derivative. So we end up with 210x to the power of 4 minus 48x, and our fourth derivative. So we end up with 840x to the power of 3 minus 48. So now looking at exercise 8.2, we're doing the same thing, but we have a slightly more complicated equation here. So here we're thinking back to, well, we're going to write it out here. So at the moment we've got y is equal u to the power of 6. dy on du is 6u to the power of 5, and we substitute back into our equation 6 2x plus 3 to the power of 5. And now we know, well, u is equal to 2x plus 3. du on dx here is equal to 2. So now if we put in our dy on dx, here is going to be, here our we'll write it out, dy on du multiplied by du on dx. So 6 multiplied by 2x plus 3 to the 5 multiplied by 2. So here this becomes 12 2x plus 3 to the power of 5. Now for our second derivative. So I haven't left myself a lot of space here. We'll box this one out. That's my first derivative. So my second derivative, we're starting with this equation here. So we're saying, well, if we write it out the same way that we had it before, we're saying here y is equal to 12u to the power of 5. Here u is equal to 2x plus 3. du on dx here is still equal to 2. So we notice this hasn't actually changed. Our u in our brackets is staying the same. Here dy on du. Here 5 times 12 is 60, u to the power of 4, and we substitute back in. We have 60, 2x plus 3 to the power of 4. So writing this out here, we get our d squared y on dx squared here is going to be here 60 2x plus 3 to the power of 4 multiplied by 2 gives us 120. Here, 2x plus 3 to the power of 4 for our second derivative. Looking at our third derivatives now. Here, so we're using this equation here. So we have our y is equal to 120 u to the power of 4. U is still equal to 2x plus 3. Du on dx is still equal to 2. Our dy on du is equal to 120 multiplied by 4 gives us 480 u to the power of 3 here. So it's 480 2x plus 3 to the power of 3. So we say here dy on dx here is 480 2x plus 3 to the power of 3 times 2 times 6. So this goes through, becomes 960 2x plus 3 to the power of 3 here. And this is our d cubed, dx cubed here. So moving into our next equation here, we're using this part here. So now y is equal to 960 u to the power of 3. U is still equal to 2x plus 3. Du on dx is still equal to 2. Dy on du is equal to 3 times 960 should give me 2880 u squared. And we substitute back into our equation 2880 2x plus 3 squared. So now d to the power of 4y on dx, 4 here, should be 2880 2x plus 3 squared multiplied by 2. Should give me 5760 2x plus 3 squared.